Yeah. Okay. Good morning, folks. Good morning. Okay. Welcome to the Open Power workshop, part of the Micro 50. And today we have a jam-packed sessions. Three sessions under that, multiple presentations. And I hope you guys are going to be very collaborative and interactive on all the presentations, and you feel free to ask us any questions, and we will be definitely helping you to answer all the questions. And I have here my one of the organizers, Raj, is going to talk about the agenda of what we are going to do today, and then the presentation starts. Thank you. Raj.
Thanks, Ganesan. Ganesan's come here all the way from India. I'm here from Austin. I think Boston's a little bit too cold for me already now, so I'm hanging in there. So what we're going to do is we'll start off with Wen Mei's talk. We'll kick it off, and he's got if you've read the abstract, he's got a very interesting talk for us. So I think it'll probably set the stage for the entire conference. He's going to pretty much cover the whole stack end to end, and talk about some of the work that's happening in the IBM Cognitive Systems Research Center. And then we'll then go to the second keynote, and we have our IBM fellow here from Austin, and he's Steve Fields, and he's going to talk about the Power 9 roadmap and beyond. And then we'll take a break. Lots of breaks here, by the way, so we want more interaction, more discussion. And then we'll go into session 2. We'll have Peter Hofstee talk about the OpenCAPI accelerator system. So this is like a ecosystem and environment for programming accelerators on power systems. And then we'll have Dennis Foley from NVIDIA talk about the next generation NVLink and some of the plans there. Then we'll have some folks from from our IBM Research Center that's looking at cognitive IoT applications. And they're going to talk a little bit about some of the work that they're doing. We'll break for lunch, and then in the afternoon is also some really cool stuff happening. We'll have TU Delft talk about their work with CAPI, which is an accelerator type in power systems. We'll do a break, and then we'll have a panel. So the panel's about an hour long, and it's going to be very interesting. So please make sure that you do come for the panel, and hoping that all the speakers are going to be available for the panel. We'll be talking about system design issues, and it's pretty much cover the whole stack. So please do make sure that you stop by for that. We'll break again, and then we'll have Jerry Lauder from Mellanox talk about the work that they're doing with designing interconnects for cognitive workloads and data movement and all those issues. And then we'll end with a discussion on how to create an ecosystem where industry, academia, and all of us can partner together so we can try and understand the requirements for cognitive workloads and then come up with ways by which we can collaborate. So that's the agenda we have. And with that, I'll hand it over to Wen Mei for the university keynote.
Oh, yeah. All right. That's good.
Now we're in business. Thanks for coming in early in the morning. So this is 8 o'clock, 8:30 Central Eastern Time, and 5 o'clock for many of you from West Coast and so on. So I'm going to spend about half an hour talking about some of the the recent work that we have been doing to incorporate accelerated work. We have this field has been extremely active in developing all kinds of heterogeneous computing accelerators and so on, and also the field has been advancing very fast in terms of machine learned cognitive applications and so on. So one of the things that we noticed in the center called C3SR, is an IBM funded center at Illinois, we noticed that there's a huge disconnect between what the workloads really doing and how they can use the accelerators and the various technologies. There's still a lot of gap, and I'm going to be talking about some of the things that we are doing and some of the things that still need to be done in order for the workloads to connect really deeply with all these accelerators. So this talk is actually prepared in collaboration with Jinjun Sheng, who's my IBM counterpart. We co-direct the center of this research, and then Abdul Dakat, Chan Lee, and Carl Pearson, who built a lot of the services and a lot of the infrastructure that you're going to see through the talk. I may not be able to answer a lot of questions during the talk. We have a pretty tight time, but we're going to have plenty of breaks and also the panel. So we can definitely use the opportunity to to discuss any of your ideas and your comments. So accelerators are a very big part of the research center at Illinois. And the vision of the whole center is that as we begin to see more cognitive applications, it's really about time for us to rethink about all the layers of this the system, applications, software, and infrastructure software and infrastructure hardware. And the idea is that when we look at some of the applications, we feel that by designing the system in a way that is much more geared towards cognitive applications, we can have orders of magnitude, not just percentages, but orders of magnitude improvement in terms of the response time, in terms of the energy efficiency, and so on for the future. And a lot of these applications need to be running in the cloud because of the data sets and so on. So we also need to make sure that these things can be connected to the cloud applications rather than being isolated just in the researcher's lab. So if we look at the experimental heterogeneous infrastructure, at the top level, we actually use IBM Bluemix and the Watson Developer Cloud. And you're going to see that two of the demos that I'm going to show today are deployed in Bluemix. So you can, as a typical user, you can actually go to Bluemix and then use some of the infrastructures that we already have developed today. And then, going down, we have the OpenPOWER and sort of the architectural infrastructure, and we use CAPI and some of the NVLink capabilities in the Minsky machines on the left. And so we actually use this machine on a regular basis for various model development and also for student education, on a pretty large scale. And then you will see some of the infrastructures are actually used to enable some of the things that we encounter some ecosystem challenges, but we're able to build some infrastructure to overcome some of these challenges. And we also have DGX1 from NVIDIA. And these two systems give us a very good, very interesting way to compare across x86 and power in quite a few areas. And then when we go down to the lower left corner, that's probably where most of you are interested. In the Tulata system, we have a CAPI interface where we can use FPGA, and so this particular system has been used, and I'm going to show a couple of the demos that we're using the FPGA to CAPI in collaboration with the CPUs to be able to do some of the inferences much faster than more energy efficiently than what we can without. So this is a quick example of how the hardware is organized for these kind of applications. So in the front, we have this video capture system. It's based on the webcam and the NVIDIA Tegra TK1. So it's kind of an embedded front-end system. And then we get into the cloud. So this is a kind of our miniature cloud setup where the edge device comes into the cloud, and the cloud is a Tuleta system based on the based on the FPGA CAPI and FPGA, and then we use the system to generate a what we call the text embedding for the images and video. So we essentially generate the text interpretation of the frames that are coming in from the system. So we have been developing quite a bit of software infrastructure for these things. So before the center formed, one of the things that we started to notice is that the GPUs have been used in a lot of applications in isolation with the CPU. That is, we copy data to GPU, we launch kernels on GPUs, and then we do things and we copy things back. But with the CAPI interface, with the OpenCAPI and so on, we start to have an opportunity to be able to do what we call the finer grain collaborative execution. For example, the data can be streamed from the network to the GPU and back, but currently a lot of these are still based on data copying. And so this particular software infrastructure is called CHAI. And it's actually an infrastructure to enable the CPU and GPU to be able to execute collaborating tasks, and then sync with fine-grained synchronization through system atomics to be able to overlap a lot of the activities as well as data movement across these components. And so there's some of these applications are the ones we are actually currently using for some of the computer vision type of cognitive applications. So I'm not going to go into the details here, but this is actually the next level of the sort of the slightly higher level of the stack, where we're beginning to enable better collaboration between the GPU, the CPU, and the FPGAs. So one of the latest papers that we're publishing is how we can have the host and FPGA to have this level of fine-grained collaboration rather than purely based on the DMA-based data transfers. So in the center, we are beginning to build a full application level driving, what we call the driving applications. Because we feel that to make the biggest impact, a lot of these accelerators and a lot of these libraries that we're developing need to be able to plug into some large-scale, real-life applications so that we can understand the real use cases of the models, the real use cases of some of these algorithms. And oftentimes it's humiliating when we see dramatic speed up in some of the experiments, and then in the real applications we don't see any speed up. And oftentimes it has to do with the disconnect between the sort of the real world frameworks and so on with our systems. So a typical application scenario that we're seeing in the very near future is that we have these kind of an edge device that would essentially bring information from the users and through the web service interface, and this will include cameras. It will include some of the interactive voice, natural language interactions, and these things will go into the cloud, and there will be a lot of these services going ongoing in the back, powering these kind of services behind the website. Video image understanding, knowledge representation, concept extraction, formal assessment, and computational creativity, natural language dialogue systems. These things are all going to be running in the back, and they're each of them have their own kind of frameworks and software stacks, and they all need to be mapped down to systems like the OpenPOWER systems here. And so we're beginning to see that there's several critical infrastructure we need to have in the ecosystem to enable this kind of flow for developers, not just for a couple researchers, but for the whole developer community. So I'm going to introduce a few of these. Obviously, you know, I'm not going to keep you here all day. You have much better talks to listen to in the next one. So I'm going to first talk about RAI. RAI. RAI is actually, you know, motivated by our needs to teach large classes of students who need to develop GPU applications. Okay, so you know what? In Illinois, we started to teach you know, these GPU parallel programming classes about 10 years ago, and we started with about 35 students. Right now, every semester when we teach these courses, we have 250 students in these classes. And it's a tremendous challenge for us to enable all the students to have seamless development environment, to use the GPUs, and then to be able to, you know, to actually have, you know, reasonable sized projects in the end for them to be able to, you know, to practice their skills. So for a student, you know what, a typical kind of question that you know, we see is that, hey, you know, Minsky just came out, okay, and this is the IBM Power 8 system that came out, you know, last year or so, and you know, they have NVLink GPUs and so on. So how do I actually, you know, try to learn to program, you know, this new system? You know, how am I going to be able to access these things? And the educators like me, you will say, here is an IBM Minsky machine that I just received, okay? And how do I enable all my class to be able to use this machine without tremendous overhead in terms of every student setup and you know, with the logging in and then learning some of the intricacies of the you know, the particular Linux setup for the for the power systems. And the big sort of community, developed community would you know, say, hey, you know, I have an open source project, okay, but I don't necessarily have a Minsky machine, but I want to enable the cloud services to use my open source project based on, you know, these Minsky machines. How do I enable that? So you know, this is what we end up doing. We built a client called RAI client, and this client is you know, is compatible with you know, pretty much all the operating systems. And most of our students use either Apple, use, you know, OS X, or use, you know, the Windows. So, you know, obviously these things would need to work. But some of our students even use, you know, their cell phones, okay, to, you know, to do some of the development. It's kind of interesting generation. So you know what? So you can download the RAI client, and then you can set up the user profile with a secret key to use the RAI services. So once you set it up, you essentially the cloud service, which in this case is the Minsky machine, it becomes just like your local machine. So you have a little client and you do the editing and so on, but you know, you can essentially use RAI to submit all your builds and all your you know, makefile requests to the service, you know, the server, just like you're actually SSH into the server and did all the stuff, you know, in that environment. But the environment is actually, you know, done in such a way that it's a very simple VI-based interface in your client. So let me see if I can get this, you know, this little thing to work. So this is a student who's working on the project. So this is the VI on the local machine, and this is the submission. This is actually the submission system that builds a Docker file underneath. The students have no idea, but it's actually a Docker, you know, build environment. So this is the student code for CUDA development. So this is also a local file on the machine. So all these editing are just local. And then you run the RAI client, and this thing submits your project into the cloud, and it builds the Docker file, it deploys the Docker file in the cloud, and then the cloud actually is served by the Minsky machine, and then it generates all the outputs that you know, that forward all the output to your local client. So this allows people to be able to use their familiar and then they can do debugging and so on through through this interface. So I'm not going to. This is already. This is available through Blue Mix, and so we're going to show you, where you can if you go on the website and just search for RAI, you will find the Blue Mix deployed version of this system. So this is the development, and okay, so this is what you just saw, and it's actually quite elaborate in the back. So we have the client, and then we have a web server, and the web server has a bunch of these low balanced workers behind it, and the MISKI machine is running one of those clients. And so when we scale the system, we just add more and more of these machines in the back. And our experience with this machine has been quite useful, because we have been, for example, 270 students in ECE 408 last year actually used this system to do their final project. And the reason why RAI is so important is because they are doing a GPU implementation of a CNN convolution layer, but then that layer needs to be incorporated into a framework, so that they can do the inference and training and so on, using the real framework based on their GPU code. So if they need to install everything about the framework on their local machine, or to try to deal with that complexity themselves, it's going to be a nightmare for any of these courses. So because we set up the Docker files and we set up all the dependencies, we essentially address all the dependencies and just allow them to to take their GPU code and incorporate and use the RAI to tap into the entire dependency for Docker generation, and that complexity is hidden from the students. And if they wanted to dig into that, they can they can see all that complexity, but they don't have to deal with all that complexity when they start the project. So this is the RAI architecture, and I already kind of briefly mentioned. But this particular architecture has hundreds and hundreds of the the dependencies of open source software. But this is what we had to do in order to be able to to give the students and the educators and all the services that we actually need to support in order for these things to be useful. So for example, database. We actually keep, in order for us to be able to grade the student projects, all their submissions, all their runs are captured into the databases. And we have another whole slew of services to automate the grading process. And essentially, we're running a competition in the class. And all the students are actually using the same data set, running their project, and they're measuring the speed. So on the minute by minute basis, you see the students changing place in their class ranking, okay, through that whole project. So the only way that we can make these things happen is by enabling a really strong architecture of services based on the modern cloud frameworks. So one of the things that may be interesting to some of the developers for Power architecture, OpenPOWER architecture, is the Docker generation. What we found out is that the Docker ecosystem for Power is still at the early stage. There's still a lot of missing Docker files, images, and so on in the field. And one of the impediments we found out is that in order to generate a Docker image, you need to run it on a IBM on a machine in that architecture. So some of the students will come to us and say, we want to be able to do this little thing for our project. This is a graduate level class now, but there's some of these packages that we could not find Docker file images for those packages that we want to use. So we said, okay, that's not too bad. We can enable this. So we build on RAI, and then essentially we build a little Docker image creation mechanism, that the students can, can prepare a Docker, a Docker, manifesto file, and then we just use the interface to through RAI to send the Docker build request to the Minsky machine that we have in the back. So then we create the images. It was interesting that after we run the course, the students and TAs created almost as many Docker images as there are out there in the field for that single class. So we said, okay, this is something useful. So we started to make that available, to our IBM, partners. So this is called D4P, Docker for Power. And so essentially, you can have any kind of client, and then you can, create the Docker image through this web service, and then you can deposit it into the to the Docker Hub. So I'm not going to run through the demo, but these are the screenshots from the demo, and then eventually just upload it into the Docker image, push the Docker image up, and then you can push it into your favorite repositories, and also we keep a sort of we also have a centralized cataloging system that people can access to find all the Power Dockers images that they need, and which is actually used by a lot of our students in their projects. So it's built on RAI, but it also has a lot of these the Docker specific the layers that we needed to build in order to enable that usage. So this is the Docker for Power page that you can find all these the images that students and other people have created, and they are available for developers. So if you're interested in developing software for the OpenPOWER ecosystem, this is definitely a resource that you should look into for you to build your more customized Docker images. So the last one that I wanted to to kind of quickly go over is that we have a lot of students who are developing machine learned models and so on for our cognitive applications. The little application that I show you was a image and video frame mapping to text space, so that we can do the image understanding. So we use a lot of these machine learned models, and also our students constantly have these conversations. Oh, so and so at this other university has this model, and that seems to be working better than yours. And the students say, oh, not clear. I try to reproduce their results, and then I can't even build. I can't even get that model to work properly with the particular framework I installed on my machine, and I had to roll back a couple generations to the version of the framework in order to be able to run their thing. And then it's not clear how that really works. So we said, okay, enough of these arguments. So, let's just do this right. So we built a Carmel service system. Essentially, we realized that all the models that people have published in the field are very much framework specific. And each framework also has a lot of these dependencies that need to be satisfied properly in order for these things to really work on your system. So we actually went through all that exercise. So we we built a web service, and this web service, let me see if I'll just kind of maybe show so this is the web service that you can access, carmel.org, and currently we have exposed Cafe, Cafe2, and MXNet, and so we're going to be exposing the TensorFlow and Pi. Not Cafe.
PyTorch?
Torch, yeah, PyTorch in the next release. So these are the frameworks that are exposed. And then if you look at the models, these are all the models that we have, collected into this framework and tested on this framework. So these are all based on, the appropriate levels of the framework versions and so on. So people can just pick these models and pick the data set and just test it, and they can upload their own data set. So this is something that you can, actually play with on your own. So, but let me just kind of talk through a few of these things that we felt that was interesting when we when we learned these things. So torch and sort of piano and so on. So one of the things that we really wanted to enable is to enable the use of all these hardware innovations. I think it's important for the audience here to be, for someone who wants to test these models to be also able to test some of the innovative hardware acceleration and so on for their model. So that's why, I'm going to just kind of skip over some, for the end users. Many of them actually just want to be able to come here and say, I want to be able to incorporate this model into my application. So how do I do that? So Carmel has an interface that it allows these things to use these models as a web service, and very quickly incorporate that into their application, so that they don't have to rebuild the frameworks and models on their own machines to be able to use that. And I think it's more important for some of the people here in the audience. For model developers, there are actually several important things that we're enabling. One is, when they publish these models, oftentimes they need to compare against other models. And currently, it's a very expensive process to be able to compare against all these other models from the research group. So what we want to do is we want to be able to, for someone to come to the website and say, I need to compare against this model, this model, this model, this model, and here's the data set, and here are the data sets I want, and then you generate a table out of it. So this is for, so that you can publish your paper out of this. And then, some of the model researchers not only care about publishing at NIPS and so on, but they want to be able to tell when real applications use their models. And for example, when you train a word-to-vec model or something, when people actually use them in the machine translation and in some of the dialogues, sort of the natural language processing-based analysis systems, how do these models actually translate into the application levels, the efficacy? So this allows the researchers to be able to see some of the application level data and say, your model has contributed into so much of the accuracy, and how does model compare against the latest models that are constantly popping up everywhere? So how do I compare in that whole space? So obviously what we do is we actually do a whole lot of analytics in the back. And every time people run the models and so on, we capture some of the results and accuracy numbers and so on for the as the kind of the background. And finally, this is actually probably a slide for most of my colleagues and people who are designing these systems. And so one of the biggest frustrations that we have, many of my students are publishing at conferences like Micro and so on. And whenever they do research, oftentimes they see that a particular hardware innovation is only evaluated with one framework, a couple models, and you have no idea how these things really perform. So what we would like to enable is that we would like to be able to plug a Gen 5 based simulation system, and also a good interface for each of these FPGA kind of researcher and GPU type researcher to plug a particular platform into this service, so that we can actually take hundreds of models and all the major frameworks and use that to drive the research evaluation, the experimental process, so that you will have a statistically meaningful result from your from your technical papers, technical papers. So so this is the goal that we have for the system innovators and developers. And so this is if you go to the website and play with it, you will see that here are some of the sort of the inferences that for the image models, and then this is actually something that my students look at all the time. This is a end-to-end distributed profile that we produce for all these models. So we actually tap into the NVIDIA CUPTI, we tap into the PAPI interface, we do the network, we use the Facebook distributed coordination, so that we can produce these timelines and show for you to download the model from the essentially from the storage, and then the input, and prepare the input. Sometimes you need to scale these inputs, and people don't really tell you much about some of these pre-processing that you need to do. And then we actually load up the model into the DRAM, and then we do the inference. So this is the inference part, and then the inference part we go down into the CUDA, the CUDA part, and then see all the the kernels and all the data copies and so on that that happens, and then eventually the post-processing. So a lot of the research are focused on this part. But it's very, very important if you want to have your research to have global impact. You need to understand, how much of that truly apply, truly benefit from the overall inference experience that the real users are going to see in the cloud, for example, right? So this is a feature that we actually are very proud of, and we're preparing a publication, for this particular mechanism. But we already started to expose that, and in fact, one of the things that that will be very interesting for some of us to see is that if we look at some of the frameworks, we will see, just do a simple inference, they will be launching hundreds of small kernels, very small GPU kernels that don't even make sense. So if you're teaching a GPU programming class and you see a student launching these hundreds of small kernel launches into the GPU, you will say, oh, these people don't know what they're doing. But that's some of the real models have been doing. So this opens up some of the really interesting research opportunities for people to be able to get real efficiency out of these systems. So if we look at what's behind Carmel, it's actually a fairly elaborate web service that takes the user input, but then in the back we generate the Docker images based on some of the work that we already have done with RAI and connect to the hardware in the back. So you'll see that we have the RAI infrastructure here, we have the hardware, and then we have the Carmel API. And one of the things that we had to do to enable these things is mostly the profiling path, because without that profiling capability, it's very, very hard for us to be able to enable the system level research that we want to enable. So that's a very, very quick the introduction. So what I would like to summarize is this. In the next few years, we're going to see tremendous level of innovation from the system vendors, and this is actually what I call the the new golden age of computer architecture, because of the slowdown of the Moore's law, because of some of these the power problems. Many of the things that we know were interesting over the years, but we killed as a research community. Reconfigurable computing and acceleration, and a lot of these fine-grained parallel computing. They are becoming more and more important. People are beginning to build very, very innovative acceleration capabilities in the memory, in the storage, right? And all these things, are going to, if we're going to want to have these things to have a real impact on our industry, on our future research, we need to be able to connect these things to the end applications. And we are seeing in the field that there's tremendous interest in developing these new cognitive applications, and many of these applications are requiring very large amount of data. And whenever you have this large amount of data, you really will be looking at cloud services. The data, you can't afford to move that data all the time through these different clients. So that's why, unless we can efficiently and effectively connect these acceleration capabilities to the web services in the future, most of the research will die. This is what I call the isolated, the vine that eventually will just die. But so that's why we spend so much effort, enabling people to develop their application, develop their accelerated technology, develop their libraries, develop their application code for accelerators in the context of these cloud services and with a smooth deployment path into the cloud services. And we also want to make sure that in the future, whenever system vendors and chip vendors produce these very innovative capabilities, we want to be able to deploy them into these web services very, very quickly, so that we can benefit from these opportunities. So I'm here. So so you see me, but I want to make sure that you see the pictures of my main collaborators. So Jinjun and I have been working on almost all these services and applications. Started early last year. Abdul is the one who built the first RAI infrastructure single-handedly. He's an amazing system builder. He's one of those grad students that you wish they will stay in grad school forever, but he's graduating soon, so he will be looking for a job soon. And Chan is here for the for the workshop, for the women's engineering workshop. So she will be around, and can look her up for some of the questions. And Carl Pearson is the one who is the expert in a lot of these the low-level interconnect measurements, and how you can connect with the various protocols and so on. So that he has enabled some of the the profiling and measurement capabilities for us. So behind us, there's a fairly large team. So this is the picture of all the faculty and all the grad student postdocs and all the undergrad students who have contributed in some way into this project. So many of them also have been active users, because many of them are actually model developers and application level developers. So they have been also kind of giving us good feedback about what needs to be done. So thank you very much for your attention, and I think we may have we may be just right. So maybe 2 minutes.
Yeah, maybe
right?
One or two questions.
So if you have any question, we can answer. Otherwise, if you want to think about it, I can answer your question during the coffee break. Yes.
So for systems research, did I miss? Can you put your FPGA bit stream into that framework?
Yes. Yeah, that's exactly the point. So what happens is that let's say the typical path that we have now is that we have the FPGA board in our Toledo system, and then we connect that to through Snap Cappy Snap to the to the sort of the rest of the system, and then we expose that as a library, as a library function that typical people who are trying to use a framework. The framework has certain way of connecting to these, let's say, convolution layer and so on. So we make that connection so that you can have the real application to use yours.
Any other questions?
Yes.
So what if I have a new design of FPGA? Then I basically have a different layer of interface that's high-level functions required.
Yes.
So how does this integrate to your system?
Yeah, unfortunately, so if you have your high-level interface, you can actually just use that high-level interface, and especially you can go through the PCIe path, right? But if you want to use CAPI, you will still need to redo your interface so that you can use the CAPI for, let's say, for your fine-grained queue kind of things. So that's why we're building this Chai library, because we realize that a lot of people will have similar challenges. So what we like to do is we like to have a higher level library rather than the low level, just the CAPI snap interface for you to connect to, because that will be several months of work before you can convert that into the OpenCAPI. So that's one of the things that we're currently building and trying to enable and release.
So I have one quick question.
Yes.
So you spoke about the system tracing. So I was just curious if you were also looking at sampling the performance counters,
Yes.
like NV-Prof, and doing
Yes.
things with that.
Absolutely, absolutely. So in fact, I did not show the cache numbers and so on, but they're already in there. So when you go to the live operation, when you click on some of the things, it will actually show you, for example, some of the the GPU at the GPU level. There's some of these counters at the CPU level. There are certain different types of counters that will help you to see what your occupancy and what some of the the specific things that you need in order to explain. For example, we talk about the very small kernel launches. Right, so the kernel launch overhead is actually the bottleneck for those things, and you can actually see that in those measurements.
Yeah. So in the lab in Austin, we've developed this GPU visualization tool
Yes.
that shows the data movement on NVLink between the CPU and GPU and
Yes.
things like that.
Yes.
So we're going to try and see if you can open source that, so you guys can also use it.
If you make it available, we would love to interface with that. So those are the kind of things that really provide value, especially if we can incorporate that into our graphical interface. It will make it very useful for a lot of developers.
Thank you. Thank you. Let's thank Wen Mei.
Thank you.